Hello, good morning to everyone. My name is José Enrique Ramón and I belong to the construction department of the Instituto de Ciencias de la Construcción, Eduardo Torroja, and together with my colleague, Dra. Isabel Martínez, we work within the IXMA group in the development of non-destructive techniques to evaluate the durability of concrete structures. In this session, we will review the electrochemical techniques that we use to evaluate corrosion in reinforced concrete, both in the laboratory and on-site. But before getting into the subject, it is important that you understand the importance of these techniques. For this, I give you a small case study. You see two concrete specimens with embedded reinforcement, right? Well, which of the two specimens, A or B, do you think is corroding more? You probably think that specimen A, since it shows rust stains on the concrete surface. Okay. However, when we break the specimen to see the real state of the reinforcement, we see how the one that a priori seemed more corroded, specimen A, inside the steel remains practically intact. Only a few small rust spots appear. In this case, the damage is very minor, even though the visual signs seem to indicate otherwise. Surprisingly, when specimen V was opened, it was observed that the steel was in a much more advanced state of corrosion. Specifically, the corrosion is of a homogeneous type as a consequence of concrete carbonation that had not shown external signs so far, being a more internal corrosion. So, the conclusion is we should not rely on appearances, so we need an alternative to visual inspection. Okay, what options do we have? Well, there are a number of techniques aimed at evaluating the initiation stage. That is determining the diffusion rate of the aggressive agents to predict when they will reach the rivers and therefore the corrosion problem will start. In short, trying to detect the problem in advance. The problem with these techniques is that they are generally destructive, since they involve usually extracting cores to perform the different tests, such as the phenolphthalein test to evaluate the carbonation depth. And in addition, they are usually implemented when first corrosion signs appear, that is, in the propagation stage, when it's too late. In another line, there are non-destructive electrochemical techniques, which leave practically no trace in the structures when implemented. These are the ones we will deal with in this presentation. These techniques focus on the study of the corrosion state of the structure. They are intended to detect whether the propagation stage has started or not, and to find out at what point we are, that is, how serious is the problem, in order to choose when and how to intervene in the structure. Electrochemical non-destructive techniques are also useful to check the effectiveness of corrosion repairs. The aim of electrochemical techniques is to be able to measure some of the standardized key parameters, the interpretation of which will give us an idea of the corrosion state. On one hand, there is resistivity of concrete and corrosion potential. Two qualitative, not quantitative, qualitative parameters, What does that means? They only indicate whether there is corrosion or not in terms of probability. Almost certain there is no corrosion, 10% of probability. Maybe there is or maybe not corrosion, 50% probability. Or certainly there is corrosion at 90%. This is the idea. This is like rain prediction. We know the probability that it will rain tomorrow, but we don't know how much it will rain, whether a lot or a little. The advantage of this technique is that they are quick and relatively simple to implement. For example, when applied on site, they provide in a short time a corrosion risk map that gives an overview of the structure condition. This information can be very useful to select the critical points to be analyzed more thoroughly or to be evaluated periodically. If what we want is to quantify corrosion, that is to know how serious is the problem, we must use corrosion rate measurement techniques. This parameter expresses the deterioration rate of the reinforcement by corrosion. That is the rate at which the steel section of reinforcements is being lost. This parameter is very important since it is used in durability models to estimate the lifespan of the structure. That is how much time is left before the end of the service life. As we will see below in the detailed explanation of each of the techniques, resistivity is used to evaluate the condition of the cover concrete of reinforcement. That is like an indirect measurement. However, corrosion potential and corrosion rate are techniques directly evaluate the corrosion in the reinforcement itself. Okay? We will also see how all three parameters can be evaluated both in the laboratory and on site using appropriate techniques. Laboratory studies are usually carried out in the field of research to analyze the durability, performance of new materials such as concretes with additions or corrosion inhibitors for use in both new constructions and repairs. As already mentioned, the implementation on site is intended to evaluate the corrosion state of structures in order to establish when and how to intervene, as well as to check the effectiveness of previous repairs. Okay, let's start with resistivity. The electrical resistivity of a material is defined as its ability to withstand the transfer of ions subjected to an electrical field. It is obtained as the ratio between the applied voltage and the resulting current multiplied by a geometrical factor that usually depends on the size and shape of the sample, as well as the distance between the pools or the electrodes of the test device. Electrical resistivity is largely dependent of the microstructure properties of concrete, such as pore size and shape of the interconnections. Therefore, the magnitude of this parameter, usually in kiloohms per centimeter, is linked to the capacity of the pores network of concrete to facilitate the diffusion of abrasives and consequently to the corrosion risk. A very permeable porous network will have low resistivity and high corrosion risk. On the contrary, very compact network will have high resistivity and low corrosion or negligible corrosion risk. However, in addition to concrete porosity, there are a number of factors that affect the resistivity measurement most notably the water saturation degree, concrete temperature, specimen geometry, and the type of the electrical signal used in the test. Many of these parameters or factors can be controlled or corrected during the tests, so that the resistivity measurement can be linked primarily with concrete porosity. This is the case of laboratory studies, where the usual objective is to evaluate the durability performance of a specific type of concrete, and these are standardized tests, okay? And the aim is to eliminate all variables other than concrete porosity. Therefore, cylindrical specimens manufactured with specific geometry are used, or cores extracted directly from existing structures, the latter being a destructive test, okay? To eliminate the variable humidity, a conditioning process is required, which consists of saturating the specimens with water using a vacuum system. In addition, these tests are usually performed under controlled temperature in order to correct or to eliminate its influence in the measurement. The most commonly used laboratory method for measuring resistivity is the direct or two electrode method, which is regulated by these two standards, and this method uses two metallic electrodes or plates placed in parallel at the ends of the concrete sample. To ensure good electrical contact, a wet sponge is placed between the electrodes and the sample. For resistivity calculation, the electrical resistance between the two electrodes is measured using alternating current, and a self-factor again is applied, which depends on the cross-sectional of the specimen and the space, the separation between the electrodes. The prescriptions of the standards are rarely followed by researchers, because they usually prefer to use the most suitable instrumentation setup for the purpose of the work, using different types of electrodes, such as stainless steel or copper plates, meshes, etc. Another widely used method is the Wenner or 4-electrode method, also standardized. This method uses 4 electrodes placed in a straight line and equally spaced. The two other electrodes send current to concrete, while the two inner electrodes measure the electrical potential. The electrical resistance is obtained again as the ratio between the measured voltage and the applied current, multiplied again by a geometrical factor that only depends on the electrode spacing, the parameter A. Okay. With this method, a surface resistivity measurement is obtained with closely correlated values, although generally higher, as you can see, with respect to the bulk electrical resistivity obtained by the direct method, the previous one. Different studies, including some of our own, have shown that the Wenner method provides values about 3 times higher than the direct method. This is recognized and assumed because the advantage of this method is that it's much simpler than the direct one, since there are portable sensors that perform the measurement without the need of to place sponges or connect any wire or any cable to the river. In fact, this has led to the method also being extended for use in on-site on-site measurements. The 4-electrode sensor is placed directly on the area to be evaluated, thus avoiding the need for coding, and is therefore considered a non-destructive method. However, it should be noted that the method was initially designed to evaluate mass concrete elements, so the measurement reliability may be reduced by the presence of reinforcement embedded in concrete. To avoid this, the measurements should be performed in reinforcement-free areas, and it is recommended to replicate the measurement by placing the sensor in 2 or 3 different positions. More methods. Yes, there are another method for on-site measurements. It is the well-known method of the disk method. It is based on the measurement of the electrical resistance between the reinforcement itself and the metallic disk of known diameter that is placed superficially parallel to the river on a wet sponge again. In this case, the geometrical factor to convert resistance to resistivity is twice the diameter of the disk. Okay. A condition for the measurement to be reliable is that the cover concrete thickness, the cover depth, must be greater than the geometrical factor, okay, which makes it necessary to use a small diameter disk, usually about 2 centimeters. Okay, we have seen resistivity, and now the other qualitative electrochemical technique is the half potential or corrosion potential, which came into widespread use around 1970. In this technique, the electrical potential of the reinforcement is analyzed, since this potential becomes more negative when the corrosion process is more active. For this purpose, a potential difference measurement is made with a voltmeter between the reinforcement, also called working electrode, and an electrode with a stable potential known as reference electrode, which is superficially placed as close as possible to the reinforcement, to the working electrode, to minimize the ohmic drop generated by the high concrete resistivity. This is important. The reference electrode is connected to the positive end of the voltmeter and the reinforcement to the negative one. That's a very simple technique. The potential measurements will always be qualitative, since the value recorded is linked with the risk or probability that corrosion is occurring. The more negative its potential is, higher the corrosion risk, establishing as a general rule 3 risk levels. Low, only 10% of corrosion probability, uncertain, 50%, and high corrosion probability, 90%. As you can see, there is no single criterion for values, but they depend on the reference electrode you are using, since there are several types, we will see later. Here are some of the most used ones. As each electrode has a specific known potential, it is easy to make conversions to refer the measurement to the desired reference electrode. Simply add or subtract the difference between the 2 electrodes to be compared. The first electrode used in laboratory studies was the normal hydrogen electrode. However, it is very complicated to instrument and can also be dangerous, since hydrogen is an explosive gas. Therefore, other types of reference electrodes have been devised that are easy to handle, such as the calomel, saturated calomel electrode, or the silver chloride electrode. They can be easily prepared and are inexpensive and stable. But gradually the calomel electrode is no longer used because it contains mercury, and silver chloride is the one that you can find in most laboratories. It consists of a silver wire embedded in a chloride paste being immersed in a potassium chloride solution, okay, and that maintains a stable unknown potential. This is the principle of any reference electrode. All this is inside a glass pod with a porous ceramic membrane at the measurement end. It is evident that this type of electrodes are fragile, so their use is limited to laboratory field, usually for solution studies, although also for measurements with concrete samples, in these cases to facilitate the electrical contact and to accommodate the electrode. Again, a wet sponge is placed between the specimen and the end of the electrode. Okay. For some measurements, the electrode design is more robust, although the operating principle is the same. Okay? There are several types of electrodes, including the silver chloride one. However, the most widely used is the copper sulfate electrode. This, you can see that, because it is the cheapest and simplest one. This is again a stable reaction between a metal, in this case a copper wire, and a solution, in this case a copper sulfate solution. There is here a polymeric pod is used, and the porous membrane is much stronger. This results in a robust electrode that can be used comfortably and without risk of breakage for field measurements. Okay? The only requirement of these electrodes is that a periodical maintenance is required to check and replace, if necessary, the internal solution. So, the corrosion potential measurement is a simple technique. You simply need to know which reference electrode are using. However, when interpreting results, we must consider a number of factors that may affect the reliability of the data. In some cases, the criteria established in the standards may not be applicable. Let's look at the most relevant ones. First, one of them is the oxygen concentration on the rubber surface. A decrease in oxygen concentration will result in a more negative reading of the corrosion potential. For example, the steel reinforcement on the dense concrete cover with low permeability will have a more negative corrosion potential than that of a porous concrete with higher permeability. But this negative reading, this is important, doesn't necessarily indicate a high corrosion probability. It's only a distortion of the measurement, but it doesn't mean that the corrosion risk is higher. The measurements should also be evaluated with cathodic inhibitors, okay, as they cause the corrosion potential again to shift to more negative value, but it doesn't mean an increase in corrosion risk, as a reduction in the corrosion severity is normally achieved with these inhibitors. Okay? In the case of epoxy-coated and galvanized steel reinforcement, the ISTM standard clearly indicates that the half potential technique is not suitable. Epoxy-coated bars do not provide a good electrical connection to the measurement circuit, and a true and stable potential reading may not be achieved. And in the case of galvanized steel, the measured half potential is no longer the corrosion potential of the steel, but the mixed potential of steel and zinc, is the metals normally used in galvanized. Therefore, in understanding how the various factors influence the measurement is the key to meaningful interpretation of this technique. That's important. Okay, we have seen the qualitative techniques, both resistivity and corrosion potential. That can be the advantages that can be measured quickly and easily, but are qualitative. So they are often used in conjunction and complementary to corrosion rate measurement. Okay. The parameter corrosion rate is the parameter through which to quantify the corrosion process. That means to determine the deterioration rate of the reinforcement by corrosion, that is the rate at which the rebar section is being lost. The corrosion rate is expressed as loss of thickness in micrometers per year. But in practice, the corrosion rate is not measured directly, but is equivalent in terms of current density, corrosion density, ICOR. This is the parameter we usually measure. As you can see, it's directly proportional by applying a constant to the corrosion rate. Okay, as we are seeing, electrochemical techniques base this measurement principle on analyzing the reinforcement response when an electrical signal is applied. So it's usual to use this parameter. Okay, as expected, the corrosion density is directly proportional to the corrosion level being established in standards. As with the rest of parameters, difference levels according to the recorded value. But in this case, we no longer speak about probability or corrosion risk. We talk about the corrosion degree or corrosion level. That is, we are quantifying the severity of the problem. To obtain the corrosion density, the reinforcement must be polarized or disturbed by means of a 3-electrode cell. That is a measuring cell composed of the reinforcement to be evaluated, which acts as the working electrode, a reference electrode as the used in the corrosion potential measurements, okay? And finally, the third element is a counter electrode, usually a non-polarizable element such as stainless steel or graphite. Concrete is the electrolyte in the electrical measurement circuit. Okay, and here we can see a real assembly of one of these 3 electrode cells for laboratory measurements. As you can see, the rebar here is embedded in the concrete sample of manageable dimensions. The reference electrode in this case is the silver chloride electrode, special for laboratory use, and the counter electrode is a stainless steel mesh placed on one side of the sample. It is possible to place more than one rebar on the specimen to increase the reliability of results. Okay, this is what we usually do in laboratory studies. So to polarize the rebar, an excitation signal, electrical signal between the working electrode and the rebar and the counter electrode is applied with a potentiostator or galvanostat. While the perturbation is applied, the working electrode potential is recorded with reference as well as the current intensity flowing between the working electrode and the counter electrode. Okay, both parameters, because from the current and the potential recorded, the corrosion current density is obtained. But the truth is that there are different measuring techniques which differ in the type of disturbance of electrical signal applied. One of the first techniques was the Tafel technique. In this case, the perturbation consists of a controlled modification of the working electrode potential, and the current response is recorded. From the semi-logarithmic representation of the current response versus the applied potential, the corrosion density is obtained by the Tafel extrapolation method. It consists of extrapolation and intersecting the linear sections that appear in the curve, both in the anodic and the cathodic potential branch, when the perturbation is high enough. And this is the main problem. The main problem with this method is that it is slow and applies high perturbations, so it can disturb the reinforcement in an irreversible way. For these reasons, the Tafel method has been replaced by other techniques. The main alternative is to determine the corrosion density by the linear projection resistance, the RP. The difference with respect to the Tafel method is that the applied perturbation is much lower, between 10 and 20 millivolts only. So there is no risk of irreversible damage of the rivas. The projection resistance is obtained directly as the ratio between the recorded potential and the current. Using a simple formula, projection resistance is converted into current density, the parameter we are looking for. But the main problem with this method is to be able to compensate the ohmic drop, again generated in the cell because the high resistivity of concrete that is applied. If this phenomenon is not compensated or corrected, the RP, the projection resistance, will be overestimated and will distort the corrosion rate calculation. One technique that solves this problem is the electrochemical impedance spectroscopy. This is one of the techniques based on the projection resistance method that is most widely used in the laboratory, due to the large amount of information it provides. The principle of this technique is to apply an alternating current signal of a small amplitude, usually between 5 and 20 millivolts, to the working electrode at different frequencies. The impedance of the electrochemical system is collected and then it is fitted for its interpretation and analysis to an equivalent electrical circuit, mainly composed by resistors and capacitors. Impedance is the equivalent to resistance, to electrical resistance, when alternating current is used. From the equivalent circuit modeling, apart from the projection resistance and the ohmic resistance to be compensated, additional information about the presence of surface films can be obtained. This makes impedance spectroscopy the standard laboratory technique for studying protective coatings and corrosion inhibitors. However, in practice, interpreting the results may be difficult, and the use of an equivalent circuit which can change according to the steel condition, it should be modified depending on the study, makes the technique difficult to implement for on-site. So this technique is usually for laboratory studies. This has led to simpler techniques gaining wider acceptance. This is the case of the galvanostatic pulse technique, also based on the linear polarization resistance method. In this case, to cause the perturbation, a current pulse of order of microamperes is applied between the working electrode and the counter electrode. In parallel, the potential response of the rebar is recorded with the reference electrode. This is a typical response we can record with this technique. As you can see, the ohmic resistance is compensated immediately at the beginning of the test, so that at the end we have the effective polarization, a parameter which, when divided by the applied current, gives the polarization resistance we are looking for. In addition to being simple, this method is really fast, since the pulse rarely lasts more than 50 seconds, depending on the concrete and the steel condition, but rarely in practice lasts more than 50 seconds. In exchange of this advantage, the measurement loses some reliability, since a fixed value of 26 millivolts is assumed for the parameter V in the formula. And it is known that this value should not always be adopted, but to know the real V value, additional tests should be performed, which will lengthen and make the measurement more difficult. So the advantage of speed and simplicity of this technique far overcomes the possible reduction in reliability, which in some cases is totally assumable. So in practice, polarization resistance using galvanostatic pulse technique is one of the most widely used methods. In fact, the majority of on-site measurement techniques are based on this method or a variation of this method. But the important thing here is to know how the cell to measure corrosion is, in this case, for on-site. Well, the working electrode is always the reinforcement. Here you have an scheme. It's the reinforcement the working electrode, obviously, which would have to be accessed by punctually removing the covered concrete in a single, very small area of the structure to connect the measuring device. In this way, on the other hand, the reference electrode and the counter electrode are integrated in a sensor which is placed superficially on the concrete. The counter electrode should have a flat shape so that it can be easily supported. Normally, the counter electrode is a stainless steel disc or ring. In this way, the potentiostatic pulse method, before described, is applied, and the corrosion current density can be obtained simply. However, the main problem with on-site measurement lies in the difficulty to apply the test to a delimited and no reinforcement area, since its value must be introduced in the equation. Usually, if we apply the machine with this device, we don't know how much area is affected by the test, so we need something to delimit the test to a concrete area. So to solve this problem, the word ring modulated confinement method alert it sounds very complicated, but this is the method which allows to confine the test in a specific river area. Okay, for that, a ring known as a word ring is incorporated to the sensor around the counter electrode, through which a current opposite to that applied by the counter electrode is applied through the word ring. This way, the signal is confined to a controlled and known reinforcement area, which allows the calculation of corrosion density. To ensure that confinement is correctly performed to the desired area, the most advanced technique or devices use two additional sensors or electrodes, S1 and S2, in charge of controlling at all time the current to be applied by the wiring so that the confinement is correctly performed. It has been shown that if the confinement is not controlled by these two sensors, the results obtained are erroneous normally. Another alternative are sensors based on the potential attenuation method. This involves applying, in this case, a potentiostatic pulse to the river, normally about 100 millivolts, and recording how varies the effective polarization of the river as we move away from the counter electrode. To do this, the sensor includes, in addition to the central reference electrode, includes 3 additional reference electrodes placed at different distances from the counter electrode. These 3 you can see there. The objective is to detect the critical length from which the reinforcement is no longer affected by the test, and thus to know the still area to be evaluated, that is being evaluated. With this data, the polarization resistance and the corrosion density is obtained. The polarization resistance, again, is the ratio between the applied potential and the current recorded at the end of the test. These type of sensors are very useful to evaluate especially wet concrete or even submerged one. Okay, once the electrochemical techniques are known, let's review the main steps to follow when performing an on-site inspection. The first thing we always do, obviously, is to perform a visual inspection of the structure to identify the areas of greatest interest in which to carry out the test. Normally, we select areas where first signs of corrosion already appear, if it's the case, such as cracks or rust spots. Also, areas that may have been exposed to aggressives as chlorides, and it is also important always to analyze apparently healthy areas as a reference. Okay. The next step is to locate the reinforcement using normally an electromagnetic river locator in the areas to be evaluated. Marking its position and depth on the structure itself. It's essential since it conditions the way in which the different sensors and electrodes used in electrochemical techniques are placed. Thirdly, we choose a point on a structure in which to punctually remove the covered concrete to establish electrical connection with reinforcement. If further inspections are expected, it is advisable to keep the connection inside a waterproof box or similar that can be easily accessible later. An important step is to condition the concrete surface in the inspection areas. If there is any type of waterproof coating, it should be removed. And something very important, wetting the concrete to minimize the ohmic resistance and to guarantee that the saturation degree of the poured work is similar in the different points so that the information obtained is comparable. After that, corresponding sensors can be placed on wet sponges to guarantee the electrical contact and to overcome possible concrete irregularities. And usually we first perform the phase test measurements, as we have seen before, resistivity and corrosion potential. Then the corrosion rate test, finally, in which the diameter of the reinforcement must be entered to make the measurements as accurate as possible. And the last step is to interpret results, checking that information obtained from the three parameters, resistivity, potential, and corrosion rate, is consistent. That is, if the resistivity and potential indicate low corrosion risk, the corrosion rate would not be expected to be high, and vice versa. If it's not the case, the measurements should be reviewed and repeated if it's necessary. Okay, there are corrosimeters. Corrosimeters such as Record 8, a commercial device, or NAVE ACM, a recent development carried out by our group, which integrate the different sensors and techniques described for on-site corrosion assessment. Here we can see as an example the results obtained on the on-site inspection of a reinforced concrete wall, which in this case with the NAVE ACM corrosimeter. In the resistivity map, the highest risk areas are identified as the most red or orange ones, as on the rest of the maps also. In the resistivity maps, the higher risk area are identified on the top of the wall and some parts close to the ground. Analyzing the corrosion potential map also appear areas of higher risk in these zones, the upper part and close to the ground. However, the corrosion rate map shows only the upper part of the wall as the risk one. These results are consistent with the exposure conditions, since the lower zone presents an higher risk due to the fact that it has higher humidity because its proximity to the ground, obviously. However, so far there are no aggressive ions that trigger corrosions, as we can see in the corrosion rate map. Here there is no corrosion level height or similar. On the contrary, the upper part of the wall was chloride contaminated during concrete manufacturing. That's the reason why the upper part is the only one with part on where corrosion rate in this case moderated level has been recorded. Okay, this example demonstrates the importance of always analyzing the different corrosion parameters together, with corrosion density, of course, being the most important one to prioritize. Even more so, considering that corrosion rate is the parameter used in the prediction of the service life of structures. For this purpose, models based on the corrosion penetration damage are used, where the corrosion density intervenes. To reliably calculate the corrosion section loss, okay, we must know the reinforcement diameter and the penetration factor alpha, which is obviously higher for pitting corrosion. And the most important, we should introduce a corrosion density value as accurate as possible. In this way, it is possible to make a future prediction of what the penetration damage will be at a given time, if we know the rate at which the process will take place. Therefore, the closer to reality the corrosion rate value entered in the model, the better the prediction. It should be taken into account that the corrosion rate undergoes oscillations over time. as a consequence of temperature and humidity seasonal variations, obviously. Therefore, the usual practice is to take an annual average value. To obtain a representative annual value, the corrosion rate, it is necessary to carry out periodic inspections. In this way, it's possible to know the trend of the corrosion process, which will facilitate its early detection also. In this line, the use of sensor monitoring system is of very great interest. The main advantage of these systems with respect to the on-site inspection techniques are their ability to monitor multiple zones continuously and remotely, their ability to identify the trend of the corrosion process, so predictions will be more reliable, and in addition, a significant reduction in inspection cost is achieved since on-site technicians are not required for each measurement. Okay, at this point, in the next presentation, our colleagues of the Universidad Politécnica de Valencia will tell you more about this strategy, okay? So, in addition to electrochemical techniques, which were the focus of this presentation, there are a number of techniques, also non-destructive, that provide complementary information of interest when evaluating concrete structures on site. Even though they are not intended to directly evaluate the corrosion phenomenon, we consider that they are important in the field of pathology detection in a structure. Here we are going to see only two techniques. We consider they are important. The first one, on the one hand, is the ground penetrating radar. In the field of construction and building, the ground penetrating radar is of great interest due to its ability to determine the depth, position, and size of objects or interfaces hidden within a structure. For this purpose, we use an equipment with two antennas, the transmitter and the receiver, both placed on the surface of the element to be evaluated. The transmitting antenna generates a radio wave that travels through the material until it reaches an interface between two materials with different electrical characteristics. Part of the signal is then reflected. The receiving antenna records the reflected signal, and it is stored and plotted on what is known as a radargram, a graph showing the depth and distance at which the wave has been reflected. By analyzing the radargram, the reinforcement position can be identified, and the covered concrete can be evaluated to determine its thickness and to detect possible heterogeneities or defects hidden. Ground penetrating radar equipment is usually coupled to a rolling system to facilitate the inspection of large structures. Among the possible applications, here is an example of a real radargram in which the river position is clearly identified through the hyperbolas of equal height that appear and have been recorded. Okay, thank you. It is also used for the detection of varied pipelines, or in this other example, to analyze the thickness of the different layers of a pavement. Also, hidden defects can be detected, such as lamination in pavements or voids under reinforced concrete elements also can be detected. The other interesting technique is infrared thermography. It is the science that studies the collection and analysis of thermal information. Thermography is a non-contact technique that allows the evaluation of surface pathologies undetectable by the human eye. So thermography is considered a non-destructive technique that has multiple applications. In fact, in this COVID time, thermography is used every day to control our body temperature. Apart from this COVID time, this COVID application is a medical application. The technique is used for many maintenance uses, research, quality control, process monitoring, etc. But how does a thermographic camera actually works? It captures the invisible infrared radiation emitted by the body's surface and transforms it to visible information, namely temperature images. The camera captures radiation from different sources, emission, reflection, and transmission, but most building materials are opaque, so transmission can be omitted. The reflection radiation can be easily corrected to keep only the emission, which is what the camera will transform to temperature. To perform this transformation, we must know the emissivity of the objects. And what's emissivity? Is the body capacity to emit infrared radiation. We could say that the higher the temperature, the higher the radiation, but the material emissivity also comes into play. So the higher emissivity, the more radiation will it emit. Therefore, the combination of temperature and emissivity determines the object radiation detected by the camera. What the camera does is to transform the detected radiation into temperature after eliminating the reflection part and applying the corresponding emissivity value. How we can apply this technology in buildings? The most important thing is to know that this technique can only detect pathologies or defects that cause temperature variations on the surface of materials. These temperature variations must be sufficiently high, at least 3 Celsius degrees. For this reason, it is possible to active with head materials to improve the detection capacity. And if we want to obtain a quantitative thermography, that is to know the real temperature of objects, it is necessary to know the emissivity of materials. What can be detected with infrared thermography in construction? Mainly the following: insulation defects, dampness, and air infiltrations. Quickly, we are going to see some examples of dampness detection on a roof and on a facade, air infiltrations, and thermal breaches from inside and also from the outside. So thermography is also of great interest in research. It is used to analyze for example, the hydration heat during concrete curing, also to evaluate historical heritage, and also in thermal efficiency tests of enclosures, and many more that we cannot go into there here. At least, I hope that the usefulness of these techniques complementaries has been made clear. So in conclusion, the range of non-destructive inspection techniques is wide and varied. Among the electrochemical ones, to evaluate corrosion, some stand out for their speed, others for their quantification capacity, and as we have seen, they are rarely applied individually, but are usually combined and can be complemented by other interesting non-destructive techniques, such as the ground-penetrating radar and thermography. So in our hands as engineers, technicians, or researchers is to select the most appropriate combination of techniques for each case. And that's all from my side. Thank you very much for your attention,